This is a monument to one of the greatest technological triumphs in the history of mankind. And for those of us who witnessed what happened here at 9:32 on the morning of July the 16th, 1969, it's an object that brings back, as fresh as if it were yesterday, one of the most profoundly moving events of our lives. For it was from this tower that Apollo 11 lifted off on incandescent flame and thunder to carry man to the surface of the moon for the first time. An estimated 1,000 million people watched the moon landing. And what that landing involved still somehow staggers the imagination today. Because it involved launching from the Earth, which was spinning at 1,000 miles an hour, and at the same time circling the sun at nearly 70,000 miles an hour, and launching from a point on Earth away from where the moon was, and then aiming at a point in space where the moon would be in 3 days' time. And then, after a journey of 240,000 miles, landing within 1.5 miles of the target point. Apollo is a supreme example of why technology is so often a double-edged weapon, because the navigational instruments developed to make a precision landing on the surface of the moon make child's play of the business of moving from one part of our planet to another. Those instruments are basically what takes your holiday jet to its destination virtually unaided. They also make it possible to launch an intercontinental ballistic missile carrying several atomic warheads, each one of which can be independently guided to within 100 yards of its target point. Now, what that means is that the underground missile sites of the other side are no longer safe. They will not survive attack so as to be used in retaliation afterwards. Now, the temptation, when you know that fact, is to launch your missiles first. The question is, will that happen? It's not a new problem. This is the second time in history that a major breakthrough in missile technology has fundamentally changed the situation. The last time, 600 years ago, the missile was a cannonball. And look what happened then. 15th century Europe was a place where hardly a day went by without somebody fighting somebody. But in those early years of the use of gunpowder, the cannon was more bang and smoke than real impact. Still, it frightened people enough. Then the armies devastating the countryside stopped firing stones and rubble and started using the new iron cannonballs. And life in places like this became very earnest. This is Aigues-Mortes in the south of France, built in marshland on the edge of the Mediterranean, and nothing much has ever happened here. As you can see, it's never been destroyed by cannon fire, which is why it serves as a perfect example of why most of the other places like it were. It's one of the most untouched examples of a pre-cannonball medieval fortification, and it's also quite beautiful. When this place was built in 1300, life was simple. Wraparound vision from these drum towers gave your archers complete command of anything within bowshot. Nice, tall, slim walls, proof against catapults, battering rams, knights on horseback, you name it. And if anybody should try to scale the walls, boiling oil. The cannonball changed everything. It knocked the tall walls down, couldn't miss. And if they started firing at you from long range, the only way to hit them was to get your own cannon and fire back. And that left one problem, and you're in it. If I come down there and play the part of the attacker, and you go up there on the castle walls and be the defender, I'll show you what I mean. Okay, follow me with your gun. You can see me, you can still see me, but now you can't see me. Now go to the other side of the tower. Okay, now follow me again. You can see me, you can still see me, but Now, you can't see me. So there's a blind spot in front of this round tower that you can't cover. It's in the area between these white tapes, you see? Now, if I can get my commandos in here, I can blow this wall up and there's nothing you can do about it. So, what's the best solution to your problem? You've got a hole. Yes, fill it. Build the tower this shape. And about 1450, that's just what they did.
It was an Italian idea, and it totally altered the shape of towns. This is what the new pointed rampart looked like, called a bastion. And because it made town walls look star-shaped, the new defensive layout became known as the Star Fort.
The architects that used to build these things used to come along to towns and sell the idea rather like you sell cloth. They'd say, you know, how many bastions can you afford? You know, we can give you 5, 6, 2, whatever you like. And the town would buy whatever it could afford. But you forgot the cost once you came up onto the bastions. Here you get a warmly impregnable feeling. Look around. The walls are nice and low. They're very difficult to hit. They're sloped so that any cannonball that hits them will ricochet off. And they're built in brick to withstand impact. Now, one bastion protects another. You see over there in that inlet, there would be guns over there firing along the side of my bastion, protecting me, and I can do precisely the same thing for the other bastion. And what is more, between us, we can put up really withering crossfire in this area, protecting the main wall of the fortress. Add to that scheme the island in the moat, the Ravelin as it's called, and put guns on it, and you're really wrapped up nice and snug. And should the enemy by any chance get onto that island, well, you simply get a big pile of guns on this bastion, a big pile of guns on the other bastion, and you blow them to kingdom come. That's what was so good about these bastions. You could use the guns on them so effectively.
Look, the guns in the little inlet behind one bastion covered the next, and their neighbours returned the favour. They also protected the main wall if you got past this defence. And you never even got that far. The entire town was snug behind a cat's cradle of cannon fire. You wanted straight streets to move guns and ammunition from bastion to bastion if needed, so town planning got a boost. From mid-16th century onwards, people stood a fair chance of living out their lives in safety behind their new walls. All they needed was food and, of course, ammunition.
Now, some of these places had as many as 200 guns firing about once every 10 minutes. The guns were zeroed up before they were put into position. That is to say, they were test-fired. You fire the gun horizontally and see where the ball drops. Then you raise it 1 degree, see where the ball drops, raise it 1 more degree, see how far the ball goes, and so on until you reach maximum range. Now, since you live here and you know exactly how far across the moat the enemy are, you know the angle at which your gun has to be in order to hit them. To get that angle right, you use an adapted astronomical instrument like this. It's called a gunner's quadrant. Dead simple to use. You just shove it down the muzzle and watch where the plumb line goes past the scale, so you know the angle of elevation of your gun, and knowing that, you're ready to load and fire. Well, except for one thing. Does your gunpowder work as well as it should? And that's what that rather silly pole is all about over there. Testing gunpowder was a bit like going to the fairground, because this is what you did. You took a measured amount of standard gunpowder and you put it in that cup like that, and then you put a cannonball of a known weight on top, and then you lit the fuse and stood back. And depending on how far up the pole the ball went, you knew whether your gunpowder was okay or not. Well, so much for the defenders. What about the attackers out here? Well, they had a much harder time. They had to try and get those guns on the bastions out
with whatever they were carrying at the time, the instruments they had. In general, that tended to be this. It's an astronomical instrument called an astrolabe. It's a kind of medieval astronomer's computer that can do all sorts of amazing things relating to the sky and eclipses and so on. Fortunately for the illiterate gunners, on the back it has a very simple star sighting device, which you can also use to find out how high above you those guns are that you want to knock out. You just line up the sights, read off the thing, and it says 7 degrees, so you know how high to elevate your gun. Okay, how far away are they? That's important. Well, if you take the astrolabe and turn it like that, horizontal, you end up with a device that was called a circumferenter. Here's one, and that's used for getting the distance away from you that those guns are. You line it up north-south because it's got a compass. Then you use these two sights here to draw a bead on the guns you want to destroy, and you can see from the scale how many degrees they are away from north to one side, as it were, from you here. You then go down the road a known distance and do that again. And that comes down to some very simple geometry, which they used to do on their drum heads like this. We're here. That other observation point, let's say, is down there, and we know that's 100 meters away. We just took a bead on the guns that was this much off north, if that's north. Down the road, when we did it, perhaps it would have been like that. So we know that the gun we want to hit is there. If we get a pair of compasses and use a scale, if that's 100 meters, then that's going to be about 110, and this is going to be about 105. So we know how far away to shoot if we're going to shoot from here or here. Fine. That was all right, except that while you were doing all this, they shot you. So when Leonard Digges, an Englishman, brought out in about 1560 a thing called a theodolite that did all these jobs in one go, he was a very popular fellow. This is it. See, it's got a plumb line, so you can set it up straight, and a built-in compass for pointing north. Well, the bit for finding the angle of the target off to one side of you works exactly the same way as the circumferenter. And so does the geometry bit that you do afterwards to find out how far away from the target your guns will be once you've done 2 sightings. The new thing is the part that tells you how high up the target is, this bit. With Diggs's Theodolitus, you know all you need fast enough to stay alive. What you don't know is whether you're in the right place or not, because in spite of all these sophisticated instruments, at the time, maps were a joke. Look, this is all you got. The rivers you were going to cross, a few bridges where there was a bridge, and if there was a town that was going to give you something to eat, you got a little box with a steeple on it. That's all you had. No wonder so many people got lost. Anyway, Leonard Digges and his theodolite solved that map-making problem, thanks in the main to a recent and rather unsavoury divorce case. This is the short but sobering tale of what happened to monasteries in England because Henry VIII divorced his wife, and how little Jack Horner pulled out his plum. See, Henry divorced his wife in defiance of the Pope, turned the country Protestant, and in 1536 started taking their lands and properties away from these monasteries. A, because they were Catholic, and B, because they had twice as much money as he had, and he was a bit short of cash. Now, at some places, like Glastonbury, they thought they knew how to buy a little time. The idea was probably cooked up by the abbot's steward, a certain Jack Horner. Send a pie to the king containing title deeds to some abbey properties. This rich little pie filling was supposed to make the king conveniently forget the rest of the abbey's property. Well, on the way to London, little Jack Horner pulled out his plum, one of the property deeds, and the king got what was left, which wasn't enough. So the plan failed. Henry took everything. And that's why map-making got better, because when Henry sold all those monastic lands, he kicked off a surveyor's bonanza, because all the buyers wanted their land measured first. Christopher Saxton, one of the surveyors, put his profession on the map in 1584 by producing the first national atlas in the Western world, showing almost every river and town and a rough idea of the terrain. His maps didn't, of course, include Scotland, because it was a separate sovereign state at the time. Strangely enough, John Ogilby left Scotland out of his maps too, nearly 100 years later, when Scotland was ruled from London. These were the first systematic surveys of all main roads in the country, and like this one, of the road north from London, they showed county names, towns, bridges, and distance marked by the new statute mile. And yet Ogilby went only as far as the border with all this fancy detail.
Up here in the Scottish Highlands, there wasn't anything like that. I mean, why bother, said the English. Look at it, there's nothing worth bothering about. Well, the 1715 rebellion proved that there was. And still nothing was done. Until, in 1724, the Member of Parliament for Bath, a retired Major General called George Wade, was sent up here to report on how the post-war pacification of the clans was going. He wrote back a letter saying that it wasn't, and that they were as ready to revolt as they ever had been, and that what this country needed was more garrisons, more troops, and above all, a road to move the troops around on. So the king said, OK, go ahead, and they started to work. The work took 500 men with picks and shovels, and they laid a layer of large stones, then a layer of smaller stones, and then packed the surface with gravel, and, when necessary, built drainage ditches on either side of the road. When the military road was finished, it was one of the best in Europe. And to this day, it's named after the man who built it. This is called Wade's Road.
The English were so pleased with Wade that in 1745, when he was using his road to chase Bonnie Prince Charlie, they even added a verse to the national anthem. God grant that Marshal Wade may by thy mighty aid victory bring. May he sedition hush, and like a torrent rush, rebellious Scots to crush. God save the king.
To a roadmaker, the road over Corryarrick Pass must rank as Wade's greatest triumph. It's ironic because he built it for English soldiers going north, and in 1745 Bonnie Prince Charlie used it for Scottish soldiers going south on the trip that took them to, 130 miles from London, and the banks collapsed and everybody panicked and the king packed his bags. It was the 1745 rebellion that actually finally convinced the English that they should map Scotland for their generals. And one of the surveyors on that job was a fellow called Roy, and he kept pushing for a national map of the entire island. And still nothing was done. And again it took war, this time the fear of invasion from France, to get the English to move. Finally, in 1791, the Ordnance Survey was set up, and off they went. In 1820, they decided to map Ireland. And that decision helped kick off a new kind of illumination. Because the very first measurement they wanted to take was from Divis Mountain here outside Belfast, right the way across over to that mountain in Donegal called Sleevesnacht.
You remember that business the gunners did of working out how far away a target was by drawing a triangle? That's what triangulation is. Well, Divis and Sleevesnacht were 2 points of a triangle, with the third on a mountain in Scotland. In autumn 1824, the problem was you couldn't see from Divis to Sleevesnacht because the weather was so bad. Weeks of fiddling went by, and still, every time the Royal Engineers looked through the murk, all they got was an eyeful of murk. They lit fires on Sleevesnacht, they stuck poles on it, nothing. And you can't be master of all you do not survey. So the English went rather politely hysterical when at the Tower of London, in a patriotic little ceremony, a young surveyor called William Drummond came up with the answer. The show took place in the Armoury and quite literally dazzled everybody. William Drummond had invented a light you could stick on any mountain and see for miles. The Irish problem was solved thanks to a shining example of British genius. Inferior foreign lights paled into insignificance beside the brilliance of Drummond's device, and English hearts burst with pride, because now they could measure Ireland, they could tax it better. The new light worked like this. Up 3 tubes came alcohol, hydrogen, and oxygen. These were sprayed onto a piece of limestone and ignited. Behind the limestone, a curved reflector. As the flames heated up the limestone, it would grow brighter and brighter until, in the end, it would become incandescent. When they put Drummond's limelight on the mountain, their troubles were over. By 1829, Drummond was trying to get his limelight into lighthouses, the obvious place to put it. Early tests had shown that at night, the light was so intense it cast a shadow at a distance of 10 miles from the lighthouse. But problems with leaking gas and not enough gas and too expensive gas finally convinced the authorities that although limelight was just what they needed, it was going to cost more than they were prepared to pay, so Drummond dropped the idea. Still, that wasn't the end of limelight, as I'm sure you've guessed. Well, I reckon the second you realise where I am now, you also realise where Drummond took his limelight next, into the theatre, where limelight took on the meaning it has in the modern world. Of course, theatres at the time were already lit by gas. Trouble wasn't just the stage that was lit. Many as the fairy came to grief when her dress got a bit too close to one of these open gas footlights. And whole theatres went up in flames. Carelessness, leaking gas. But it wasn't just the fires that got Drummond into the theatre. I mean, what actor could resist stepping into the brilliance of limelight? And so from 1837 on, limelight was everywhere, from pantomime to opera to Shakespeare, like Henry Irving's production of Macbeth. Got panned. Critics didn't think the limelight looked real enough. And since we've arrived at a rather theatrical period in history, let me explain what happened next the way they would have told it. And now, ladies and gentlemen, for a brief series of morally uplifting vignettes illustrating dedicated 19th century genius at work. Observe the fatal problem of the day. Rock A inadequately illuminated. Enter ships B to strike Rock A, sinking to watery grave C. In 1845, over 1,000 such incidents occurred. Solution: Rocks A need lighthouses B so that ships C may avoid Rocks A thanks to lighthouses B. Problem: Drummond's limelight demands too much gas. Solution: Volta's pile, which, as the demonstratory digit shows, is composed of discs of differing metals which give off electricity. Discharge aforesaid electricity into indicated water via electrodes, so that aforesaid water gives off the 2 gases necessary for limelight: hydrogen and oxygen. Problem: not enough electricity. Solution: Professor Floris Nolle of Belgium's amazing 1850 machine. Spin wheels carrying copper wire discs B past magnets A, so that magnets A induce in copper wire coils B enough electricity to produce aforementioned gases. Problem: Professor Nolle's company embezzles. Solution: his British colleague Holmes improves the machine. This is a giant version of Nolly's idea, carrying 96 coils, 56 magnets, and weighing a colossal 3 tons. So, by 1871, thanks to British genius, the mighty Holmes generator was powering the world's first fully operational lighthouse, carrying not the limelight, but a mysterious new source of light. So mysterious that, problem, it demands more power than Holmes can give. Fortunately, solution, Holmes is already obsolete. Because of this. 1 year before, a Belgian carpenter, Zeneby Graham, had put iron magnets A, coiled with copper wire, below and above an iron wheel coiled with copper wire, B. As wheel B spins, magnets A induce it with electricity, which in turn induce more magnetic power into magnets A, which in turn induce more electricity in wheel B, which etc., 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 etc. The dynamo produced enough electricity to power the mysterious light source which had defeated Holmes, the arc light. Well, enough of the theatrical stuff. Let me tell you about the arc light. Oh, which incidentally is that thing you've been seeing at the beginning of every program. It was the world's first electric light. You ran electricity into 2 pointed bits of carbon. As they almost touched, the current sparked across the gap and the carbon burned. The arc light made limelight look like a candle flame, and in no time it was in lighthouses all over Europe and America. And the crafty thing was, the mechanism to move the carbon rods was run by the same electricity that produced the light. A light you could see as far as the horizon. The arc light was as big a success in the theatre as it was in lighthouses. It got rid of limelight for a start. It also did something else. You've seen how change comes about in funny ways because of war or accident or climate or any number of things. Well, sometimes it also happens because all the bits necessary for an invention happen to come together in the same place at the same time. Well, the arc light turned out to be one of those bits. And the modern invention it helped to bring into existence is sitting in your house right now. The arc light was only the first bit. The second nearly didn't happen at all because of that. These are the docks at the quiet little Kentish town of Faversham, not to remain quiet for long. Early in 1847, a local factory had just started production of a new explosive. It was made by soaking cotton in nitric and sulfuric acid, a process which, the inventor assured them, was totally without risk. Everything within 1/4 of a mile was destroyed, and 21 people were killed. 10 of them exploded to bits, said the Illustrated London News. Can't have been much left to illustrate. Well, that blew it, if you'll forgive the phrase, for gun cotton and the search for a bigger and better bang for almost 20 years. And then one day in 1863, in the United States, there was a sudden and worrying shortage of teeth, a particular kind of teeth. This kind. You see, the great white hunter had been knocking off African elephants so fast that there was now a shortage of billiard balls, because you get 4 of them from one of these. So there was now a $10,000 prize being offered for anybody who could come up with a substitute for ivory billiard balls. And yes, you've guessed it, gun cotton was involved again, mixed with camphor and alcohol and compressed. And the fellow who did it was very good at pressing things because he was a printer from Albany, New York. His name was John Wesley Hyatt. And you could say his balls went down with quite a bang. The scene, a Colorado saloon. Enter a Hyatt billiard ball salesman. Now, we only know of this curious event, the only recorded failure of Hyatt's billiard balls, because the saloon keeper wrote to the company afterwards to complain about what happened the day a mysterious stranger rode into town and walked into his bar carrying a funny-looking case. At first, he and his ball seemed harmless enough. But remember, the shell of the ball was made with gun cotton, the explosive. Get it? Suddenly, it made the kind of noise you never made in a Western saloon. A noise like gunfire. Okay, so far in this final build-up of the jigsaw of invention, we've got two bits, the arc light and Hyatt's billiard ball with its explosive tendencies. The third bit comes next. It started life originally in Vienna through a very odd relationship between an Austrian artillery officer and a rather theatrical gent. The officer was teaching ballistic theory to army cadets in 1853 here in Vienna at the new arsenal. His name was Franz Eucatius, and he'd recently invented a thing to help him teach students about firing guns. It was a kind of projector using a limelight to throw pictures of a cannon on the wall. As he cranked the light round behind a glass disc with the pictures on it, each successive picture showed the ball at a different point in flight. And why Captain Eucatius matters is what happened to his projector. It attracted the attention of one of the three greatest travelling magicians in the world, a fellow called Ludwig Döbler. Döbler's audiences were very excited by his magic lantern shows, and the new Eucatius machine was just what he needed. So he conned Eucatius into thinking the whole thing was worth practically nothing, leaving the captain happily clutching a few florins, and Döbler happily palming a fortune, which he made from his amazing consecutive picture show that soon became the rage of Europe, and, more significantly, the west coast of the United States. It was in California that this guy, Edward Muybridge, took the idea of consecutive pictures one very important stage further. See, Muybridge was an English immigrant, photographer, and close friend of the governor of California, who in 1872 asked him if he'd use his camera to settle a bet he had. Muybridge agreed, and because he was a photographer, he took a shot of the preparation. The experiment took place at the Union Park racecourse in Sacramento. Did all a horse's legs come off the ground at the gallop? That was the question Muybridge had to settle. So he set up 12 cameras in a row, pointing straight across the racetrack at intervals of 21 inches, and worked by a system thought out by a railway engineer friend of his. Each camera was operated by a triggering device that was activated when a piece of thread attached to it was jerked, opening and closing the shutter. The thread from each camera shutter was stretched across the racetrack. As the galloping horse passed, it would break the thread, triggering the camera. They even put numbers across the track to process the photographs in the right order. As it turned out, the governor was wrong. All 4 legs of the horse did leave the ground. But this particular photography session did something far more exciting than just settling a bet at the racetrack. In 1879, Muybridge put paintings of his photographs onto a glass disc, shone a light through it, and then spun the disc. And the horse appeared to move. He called it his zoopraxiscope. Muybridge's zoopraxiscope is the 3rd bit of our jigsaw of invention. You remember the first 2 were the arc light and Hyatt's billiard ball. It took only 1 more piece to make up all the pieces necessary for a major invention in the modern world. And here's what caused that 4th piece to happen. If you've got single-track railways, which they did in America, you've got yourself a singularly difficult problem. You have to have trains going in both directions. That's okay because you can put one train on a siding while the other goes by, if you get your timing right. If you don't, you get trains going in both directions, but not for long. These sudden stops stopped in 1856 when a network of signalling stations was set up using the recently invented Morse telegraph system. The key sent a coded electrical signal down a wire, and when the on-off electricity got to the other end, it turned a magnet on and off, making a metal bar click up and down, sounding out the code. Now we come to the part where the jigsaw gets put together. And that happened here in this room in New Jersey in the last quarter of the 19th century. And it was done by a man who put together more jigsaws than anybody ever did, a fellow called Thomas Edison. He took the arc light idea of making it glow by causing a spark to jump across 2 carbon rods like this. Then he went through, 6,000 different carbonized materials before settling on carbonized thread, put that thread inside a glass bulb, and succeeded where maybe 20 people before him had failed because he had the one thing they didn't have, this new German vacuum pump, which allowed him to have an almost perfect vacuum inside his bulb. He then ran electricity through the thread, and there, in 1879, was the world's first commercially feasible electric light. Now, what do you do with that? Well, you remember Hyatt's billiard ball? The outer shell of that was made of a material which an obscure clergyman called Hannibal Goodwin turned into sheets, and a famous businessman called Eastman put into a camera. Celluloid. In 1886, Muybridge, remember him? Talked to Edison about his moving horse pictures, and Edison then asked Eastman if he would make him a long strip of this celluloid. And on that, he put a lot of pictures, taken very quickly, one after the other, just like Muybridge had done. He also put a lot of holes on the strip so that he could move it because the holes would get caught in a spinning wheel that had teeth in it. Down there is one of Edison's kinetoscopes in which he put the whole thing together. Celluloid, toothed wheel in there, back here the light source that would later on become a light bulb. And I don't have to tell you what that all came together to become. Roll 'em. The trail has led us to the movies. You remember how the cannonball changed things in the 15th century, causing a new kind of defensive fortification? And how the gunners used instruments to line up their guns? And when Henry VIII closed all the monasteries and sold the land, those same instruments helped surveyors make maps of everywhere but Scotland. Until Wade built his road, and they decided to map the whole of Britain, but got nowhere in Ireland, until William Drummond produced his new limelight. Surveyors could see from miles away. And how he tried it in lighthouses because too many ships were going down. But the limelight needed so much gas, Nolle and Holmes tried making it with electricity generators that Graham improved on enough to be able to power the arc light, and how this arc light was the first piece of a 4-part jigsaw. The second piece being Hyatt's billiard ball that sometimes had explosive tendencies in unfortunate places. The third piece was the projector for teaching artillery students that D'Urber made famous. And Muybridge picked up the idea to make consecutive pictures that appeared to move when they were on film. Which leaves the fourth piece, the Morse telegraph, which I haven't explained yet. The moving pictures rapidly became all the rage as the new wonder of science kicked off Hollywood and all that. The only trouble with the new moving pictures was... Now, recorded sound was already around, thanks again to Edison. You see, early in his life, he'd worked as a telegraph operator using the Morse telegraph, and he'd put together some ideas that had already been around for some time in order to make this. It's called a repeating telegraph. The Morse code signal comes in here, and as it comes in, like this, it makes that needle go up and down and make indentations on that piece of paper. When you've recorded the message, you take the bit of paper off, flip it over, put it on this turntable, so that the little indentations have now become little bumps. And when you rotate this disc, the reading head goes up and down over the bumps, and when that happens, the up and down causes on-off electrical contact, and that sends the message out down the wire. The story is that one day Edison heard this thing operating at high speed, and he noticed that it made a sort of musical sound as the reading head went over the bumps. And it hit him that that was how Bell's telephone worked. You spoke at a diaphragm, it vibrated, and you could reproduce that vibration on another diaphragm somewhere else and make speech. So Edison reckoned if he could make a diaphragm vibrate, he could make speech too. All he had to do was to make speech into bumps first. And here's how he did it. He took a diaphragm, put a needle on it, and rested the diaphragm on a strip of tin foil wound around a metal cylinder. As you turned the cylinder, it moved along. So, doing so, he shouted at the diaphragm as loudly as possible, "Mary had a little lamb, its fleece was white as snow." Then he wound the cylinder back to the start point, put the needle back in the bumpy groove he'd just made, and this time, when he rotated the cylinder, what had gone in came back out. They got that sound onto film because years before, somebody had noticed that there was a metal called selenium that gave off electricity if you shone a light at it. And the more light, the more electricity. So in 1923, somebody in Denmark got a light to flicker in response to a human voice and then exposed this strip here down the side of a bit of film to that flicker. So the light and dark patches correspond to the changes in the voice. Now, when you screen this bit of film, more or less light gets through that strip and hits a piece of selenium which gives off more or less signals, and that goes into a loudspeaker, and so movies become talkies. And that takes us to the modern invention that ends our story. Because in 1928, a Russian immigrant to America called Vladimir Zworykin took that selenium idea one stage further. He realized that if you made a square plate made up of rows and rows and rows of thousands of tiny little bits of light-sensitive metal and pointed the plate at a scene, each tiny bit of metal would react to a tiny bit of the scene. It would be like dividing a scene up, let's say, of my face, into thousands of little squares. Each tiny bit of light-sensitive metal would see darkness or darkness or darkness or half light or a lot of light or a great deal of light, and would give off a corresponding signal. Nothing, 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 something, a great deal more, a lot of signal, and so on. Now, if you use those signals to reconstruct the picture line by line by using a fluorescent screen that reacted to the signals by producing a tiny dot of light that was more or less bright, you'd get this. Come a great deal closer, you'll see what I mean. This area here, look, on your television screen. You see all those lines of dots? So, television is where this particular chain of events brings us to in the end. Well, not quite the end. It's ironic that the story of how television happened should have been told here in Edison's laboratory. Television tells us every day that we live in a world we don't understand, and yet in the main it does little to explain that world. It tells us of new products that make the products we have either old-fashioned or obsolete. Above all, if today we are aware of how fast the world around us is changing, it's because television acts as a relentless reminder of that fact. Planned obsolescence, the reason you buy a new model because they don't make last year's anymore, affects the way we get our information too. I mean, take a look at the newspapers and the TV programs of 20 years ago, and you can see how much more slick, more brief is today's treatment of the world we see. Communications technology has made it possible for us to see very much more, but we still only have the same amount of time to see it in. So does that fact accelerate change? The fact that we can be more quickly saturated by an idea or a product or an event? Does this cycle that goes interest in something, involvement in it, tiring of it and rejecting it and looking for something else, get shorter every decade? That shouldn't surprise you. Over 90% of the technologists and scientists and advertisers and salesmen that have ever lived are alive now. And they've all got a job to do, haven't they? I said it was ironic that we should be here because that overwhelming rate of change has come directly from the work of Edison and men like him. Edison invented inventing here at the world's first industrial laboratory, and he laid down precise rules for it. Is there a market for the invention? Get financial backing before you start. Publicize the whole thing in advance so when it comes out the consumers are ready to pay for it. And plough every penny you make back into making more inventions. And that is how the modern world works. So, if you believe that science and technology have given us the highest standard of living in history, or that they have trapped us inside a machine we can't escape from, we live in a situation we inherited as a result of a long and complex series of events through history. At no time in the past could anybody have known that what they were doing then would end up like this now. So, the next and last program looks at whether or not we want to go on into the future like that. And if not like that, like what? And I hope to show that you can only know where you're going if you know where you've been.